In the previous video, we talked about bar plots and pie charts to visualize categorical variables, either alone or in relationship to each other. Now we want to move on to visualization of numeric variables. This video starts with scatterplots. A study collected data on a group of students, including how many hours they spend studying per week over a term, and the resulting GPA in that term. These are both discrete numeric variables, assuming we round to the nearest hour. There are two numeric variables. This works well in a plot with two axes, because we can treat each variable as an axis. Here, the horizontal axis is the GPA variable, and the vertical axis is the study variable. Then, every case gives a value for each variable. These values now are essentially coordinates, an x and a y value. They are dots, and I can put them on the visualization. And I get this. Each case is a dot, and the cases together give all these dots. A scatter plot is perhaps the most direct way to show two potentially interacting numeric variables. All the data is here, and nothing about these two variables is hidden. Visualization is meant to show something about the data. What can the scatter plot show? When we have two numeric variables, we can wonder about the relationship between them. Is there a relationship here? Maybe, but it's hard to tell. The data does seem to fall into a triangle, which might be evidence that more studying leads to higher GPA, but the evidence is marginal. More importantly, though, this is the difference between descriptive and inferential statistics. A scatter plot is descriptive. It shows the data. To hypothesize a relationship based on this is to make an inference, which may or may not be true. And we will return to this idea in greater detail later in the course. Here is another scatter plot, this one about house prices and square footage of the sold houses in a certain city. Again, every dot is a case, a house that was sold, along with its area and its price. Here there seems to be better evidence for a relationship. Larger houses certainly seem to correlate with higher prices. This would be a positive correlation if it held. Higher values in one variable lead to higher values in the other. A negative correlation would be the opposite. Larger values in one variable lead to smaller values in the other. Again, whether there actually is a relationship is something for later in the course. A scatter plot also demonstrates something else, an outlier. Scatter plots show how the data is grouped. This data has a unique case which is very far away from the others. This is an outlier. Dealing with outliers is an important part of data analysis, and again, something we will certainly return to. Here is another scatter plot, this one from a British study about smoking. The two numeric variables are cigarettes smoked per day on a weekend day, and the age of the smoker. This scatter plot is really all over the place. Other than certain responses, 15 and 20 being more common, this looks like a pretty random spray of data, and it is very unlikely that there is any relationship here to be drawn between the two variables. Here's another scatter plot from a study of US counties that include variables of median household income and poverty rate in percentage. Again, each dot is a particular county and its value for those two variables. There looks like there might be a relationship here, a negative correlation, since higher income leads to lower poverty rates, but perhaps not a straight line relationship, perhaps something more complicated. Well, this lets me introduce a new idea for numeric data, and this is the second big idea of this video. Instead of just visualizing data, we can also do something to the data before visualizing or otherwise working with it. What do I mean by do something? Well, I mean applying some mathematical function. This is called transforming the data. In principle, I can use any mathematical function on the data. I could square root the data, or calculate 2 to the power of the data. I could apply a logarithm to the data. If I do this consistently to all the cases, I get a new related variable, a transformed variable. And there are many places in statistics where these transformations are valuable and important. It turns out that the logarithm transformation is particularly useful. I have here the logarithm base 10, which I hope and expect you are familiar with. However, there is another logarithm which is very often used in both mathematics and statistics. There is a special number written e with value approximately 2.718, and so on. Even though this is a letter, it's just a number. It's a constant. Why this number is special? Well, that's a subject treated a little bit more detail in calculus, and we don't really have time for it, but it is one of the most important numbers in all of mathematics. The logarithm with base e has a special name. It is called the natural logarithm. It is written ln instead of log e. Transformation by the natural logarithm is a very common transformation. Though this is not a mathematics class, there are pieces of mathematics that we will need to be comfortable with. The logarithm, and the natural logarithm in particular, are two of these. Please review logarithms if you have any reservations about your memory of them. Now back to the income and poverty scattered plot. Here is the same data, but with the natural logarithm applied to both variables. Every single case, I've taken the logarithm of both variables. I get a new scatter plot. The previous one seemed to have a curved line relationship, but now this looks like there might be a straight line negative correlation. Since working with a straight line, and trying to find these straight lines, is much easier than working with curves, this transformation might turn out to be wonderful for statistical analysis. For now, it's enough to know that doing this transformation is simply a thing that can be done.